Thank you very much. I thought we could begin with some counting. Of course, maths isn't only about counting, but I'm interested in number theory, properties of whole numbers. And I particularly like this way of visualizing the numbers, as it starts to give us an insight into prime factorizations. And I want to talk all about prime numbers today. So maybe you can start to notice some patterns here. And I want to talk about patterns. This isn't such a convenient way of looking for some of the patterns that I want to do, though. So I want to arrange the numbers on a slide like this. So the idea here is we can start seeing patterns. And as mathematicians, our job is to look for patterns, to look for structures, and then to understand what's going on behind the scenes. So there's lots of patterns here that we might notice, and I'm not going to be able to talk about all of them today. So an example might be, if you look carefully, so these columns, the 4 column, the 6 column, the 8 column, and the 10 column don't seem to have any prime numbers in from the basis of what we can see on this slide. But I'm not going to be satisfied with that. I'm interested in what would happen if we kept going. If we continued this slide further, what would happen? And if you look carefully, these 4, 6, 8, and 10 columns, all the numbers in those columns are even. And the thing is, a prime number, its only factors are 1 in itself. So if you've got an even number bigger than 2, it's divisible by 1 and by itself, but also by 2, so it can't possibly be prime. So in fact, 2 is the only even prime. So in its column there, we're not going to find any more primes in that column, no matter how far we go. And these 4, 6, 8, and 10 columns really are empty. So that's not the most complicated example, but gives you a flavor of noticing a pattern and then trying to understand what's really going on. Why are we seeing that? And the kinds of patterns I want to focus on today are to do with gaps between prime numbers. So in fact, that observation about even primes shows us that if we look at 2 and 3 are consecutive numbers and they're both prime, but they're the only example of 2 consecutive numbers that are both prime. Because if we pick any 2 consecutive numbers, one of them is going to be even, and we just said 2 is the only even prime number. 1, by the way, is not prime, because it turns out that that leads to a better definition. It leads to better mathematics that way, so we define 1 not to be prime. So the only pair of consecutive numbers that are prime is 2 and 3. And up near the top, these primes are bunched up quite close together. If we look further down, there's some quite big gaps. So 83 to 89, 89 to 97, these primes are getting further apart. And that makes intuitive sense. If I give you a really big number, a number this big, it's very hard for it to be prime because it's going to be divisible potentially by lots of smaller things. There are lots of smaller numbers that might divide it that would stop it being prime. It's very easy for 7 to be prime because there aren't many smaller numbers that would stop it. A number this big, there are lots of potential factors. So it sort of makes sense that these primes are getting more spread out. One question we might ask is whether we keep finding more and more primes. If we continue down, if I could fit more and more on this slide, would I keep finding new primes? Or at some point, will we hit the biggest prime number? And those are 2 very different scenarios, right? In one world, there's a biggest prime number, and from that point on, nothing is prime. In the other scenario, no matter how far we go, we keep finding new prime numbers. And it's sort of intriguing to think which of those situations it might be. So I guess that intuition about if you're a very large number, it's very hard for you to be prime is not quite enough to guess which way it goes, because maybe they're getting further and further apart, but they still keep happening, or maybe they're getting so far apart and eventually they kind of stop. But it's sort of, I can't quite make that intuition help me figure out which it should be. I could use a computer to help, but actually that's not going to get me very far. I can ask my computer, please tell me the largest prime you can think of, and it goes and whirs and clunks for a fortnight and comes back and says, here you go, here's a very large prime number. And that tells me nothing at all, because maybe it's found the largest prime number in the world, or maybe if it thought for another month, it would think of another prime number. So a computer's not going to help there. But happily, mathematics will help. And this goes right back to the ancient Greeks. So this is a theorem. This is a mathematical statement that we can prove to be true. And the theorem is that there are infinitely many primes. There is no biggest prime number. And for me, the certainty here is what's really important. So when the radio comes on in the morning with the headlines, I don't have 0.5% of my brain thinking, oh, I wonder whether today they'll have found the largest prime number, because I'm absolutely, totally certain there is no largest prime number. And the reason that I'm totally certain is because we have a proof. So for me, proof is a really important part of what we do as mathematicians. And I want to share this proof with you because proof is really important and because this is an especially beautiful proof. And it's a very well-known proof, so lots of you will be familiar with this proof already, but I hope that, like me, you will enjoy thinking about it again. And if you haven't seen this before, it takes a little bit of getting your head around first time, but it's worth thinking about. So this goes back to Euclid's sequence of books that he wrote, the Elements, his kind of textbooks that he wrote more than 2,000 years ago. And he had this beautiful idea for proving this. So he said, let's do a thought experiment. So secretly, we think there are infinitely many primes. There's no biggest prime number. Let's imagine we're in a parallel universe where there is a biggest prime. There are only finitely many primes. And let's explore the consequences of that. And it turns out you reach an impossibility. So if we're in this parallel universe where there are only finitely many primes, I can take a very large piece of paper, and on them, I can write all the primes in the world. So my list starts 2, 3, 5, 7, 11, whatever, and I keep going until I get to the largest prime in the world. And Euclid's beautiful idea was to take all the primes in the world, multiply them together, and add 1. So this is some enormous number, right? It doesn't matter what it is. What matters is how we've built it from these primes. So this enormous number must have a prime factor. Either it's prime itself or it's divisible by a smaller prime. Every number has a prime factor once you go beyond 1. So conveniently, I've got this list on this piece of paper of all the primes in the world, and I can just check which of them are factors of this large number. So does 2 divide this number? No, because it's 2 times some stuff plus 1. So this leaves a remainder 1 when we divide by 2. Does 3, the next prime on my list, divide this number? No, because it's 3 times some stuff plus 1. It leaves a remainder 1 when we divide by 3. Does 5 divide by this number? Same story. What Euclid's done is he's built this number so that it's not divisible by any of the primes on the list. And now we're supposed to feel slightly ill, because somehow we've got this number that must have a prime factor, and yet isn't divisible by any of the primes in the world that were on our list. So we call that a contradiction in maths. It's this kind of impossibility, this absurdity that arose from supposing that there were only finitely many primes, and that tells us that there must be infinitely many primes. So this little square box symbol is a symbol that mathematicians often use to the end of a proof. So don't worry if you didn't take in all the details of that, but I think it's extraordinary. When you think about it, we're proving something really difficult, right? We're proving that there are infinitely many prime numbers, and this argument is so elegant, so beautiful, that I can fit it on a whole slide. So I'm very glad there are infinitely many prime numbers. The world is a much more interesting place with infinitely many primes. There is no largest prime number. So if we go back, we can then kind of keep thinking about patterns here. I feel like I need to confess. The thing is, I've sort of slightly misled you. You know what I was saying about the primes getting further apart towards the bottom? Because if you're a big number, it's really hard to be prime, so the gaps get bigger. Well, here's the thing about the primes. Every time you think you understand what's going on, it's a little bit more subtle than that. Because if I put another row on, I have to confess that 101, 103, 107, 109, they're all prime. So yes, they were getting farther apart, but then all of a sudden, here's a cluster bunched up all together. So what's going on? It is true that on average, the primes are getting more spread out. That's a consequence of a theorem that was proved right at the end of the 19th century called the prime number theorem, which gives us an insight into the distribution of the primes. So on average, the primes are getting more spread out. But the on average is really important there, because then you get these little pockets of primes that are very close. And it's those primes that are very close that I want to focus on today. So primes, there's these primes that differ by 2, like 3 and 5, like 29 and 31, like 107 and 109, pairs of primes that differ by 2. So we know there are infinitely many primes, so the question is, are there infinitely many pairs of primes that differ by 2? And this is called the Twin Primes Conjecture. So the conjecture, the prediction is that there are infinitely many pairs of primes that differ by 2. And there are some sort of plausible reasons for thinking that this should be true. So one plausible but not super good reason is that I can ask my computer to find examples of large pairs of twin primes, primes that differ by 2. And my computer will go away and think about it, and it will come up with very large examples. We know that there are very large pairs of primes that differ by 2. That's sort of not such a great reason, though, because, as I said, with there being infinitely many primes, there's always this risk that we found the largest pair of twin primes. So a better reason is that we can kind of model the behavior of prime numbers. So if I pick a number like 61, either 61 is prime or it's not prime. We don't get to kind of toss a coin, but we can model the prime numbers by tossing a coin. So the idea is you have a biased coin, And the probability of getting a prime is skewed a bit because the primes on average get more spread out later on. We know that it should be harder for a large number to be prime. So if you do this modeling very carefully, you can make a prediction for the number of pairs of twin primes up to 1 million or 1 billion or whatever your favorite number is. So we can make this kind of predicted estimate for the number of pairs of twin primes. And then we can check that against the data that our computer has given. That's where it's helpful to know that the computer has calculated these large examples of twin primes. And the prediction matches the data we have computationally beautifully. But it's not a proof of anything because it's only this model. So we can't prove that this is exactly how the primes work. We don't yet know how to do that. But it's sort of very compelling evidence because, in particular, it predicts that there should be infinitely many pairs of twin primes. So I thought it might be fun to have a go at trying to prove the Twin Primes conjecture. Because we should be ambitious. If we take the idea of Euclid's proof, so Euclid said, take all these primes on the piece of paper, multiply them together, add 1. Nothing at all would change in Euclid's proof if instead we took all the primes on the piece of paper, multiplied them together, and subtracted 1. So we could do this, right? If I take 2, 3, and 5, first few primes, multiply them together, subtract 1, add 1, I get 29 and 31. That's a pair of twin primes. That's kind of nice, and I could keep doing that, right? So I could take 2 times 3 times 5 times 7 and add 1 and subtract 1, and I get 209, 211. The bad news is that 209 isn't prime. So Euclid's argument doesn't say the number we come up with must be prime. It says it's not divisible by any of the primes on the list we had. So as has happened here with 209, it is divisible by smaller primes. They were just too big to have been on the list. So unfortunately, we can't prove the Twin Primes conjecture by adding and subtracting 1 from this argument, which is a shame, because that would have been nice. But that's how maths goes sometimes. Mathematicians spend a lot of time trying to prove theorems without necessarily succeeding. So one of my mathematical heroes, a mathematician called Julia Robinson, who was a mathematician in the US in the 20th century. And an administrator asked her on one occasion to describe her typical week for some form or other. So here's how Julia Robinson described her typical week. Monday, tried to prove theorem. Tuesday, tried to prove theorem. Wednesday, tried to prove theorem. Thursday, tried to prove theorem. Friday, theorem false. Which sort of sounds very depressing, but it's not quite all like that. But mathematicians do spend a lot of time trying out ideas that don't necessarily get them. So I like this because it gives us more insight into Euclid's argument, but it doesn't prove the Twin Primes conjecture. In fact, the reason the Twin Primes conjecture is still called the Twin Primes conjecture is that nobody has proved it. So we think it should be true. That's why it's a conjecture, but we don't yet have a proof. I spend a fair bit of time going into schools and talking to young people about maths, and I sometimes worry that I'm giving them the impression that maths is divided into things that we know how to do because mathematicians did them a long time ago, and those mathematicians are long since dead, and things that we don't know how to do. And that's not the case at all. Mathematicians are making progress on problems all the time. So what I want to tell you about today is some of the recent progress on this particular problem, the Twin Primes conjecture. Because it gives us a bit of an insight into how progress is made at least in some parts of mathematics. And the excitement happened back in May 2013, when a mathematician called Yitang Zhang announced this extraordinary breakthrough, got mathematicians super excited, kind of progress on the Twin Primes conjecture. Zhang managed to show that there are infinitely many pairs of primes that differ by at most 70 million. Now, when you are aiming for the Twin Primes conjecture and you want pairs of primes that differ by 2, 70 million feels like a miss, right? I mean, it's a long way off. I agree. But it was the first time that anybody had managed to prove any theorem of that type before. So 70 million is a lot bigger than 2, but it's much better than infinity. It was a finite number. That was the important thing. So there are infinitely many pairs of primes where the gap between them is less than or equal to 70 million. Zhang was not a famous expert in this area of maths. He'd had hardly any publications since his PhD. He'd found it very difficult to get a job in a university. He did, by this point, have a job as a lecturer in a university in the US, but he'd spent some time working for the Subway restaurant chain, doing various bits and bobs. But whilst doing all of that, he kept up with the research literature. So he'd really immersed himself in the area. And that was what enabled him to do this. So this wasn't some idea that everybody else had missed. He'd taken what other people in the area were doing and showed just the most extraordinary technical insight and perseverance to kind of push through an argument that sort of everybody else had ruled out because they knew it wouldn't work. It's just extraordinary. And everybody was super excited, and the experts in the area checked the proof, and yep, it was all good. And then people started to think, well, can we improve on that? And in order to tell you a bit more about that, I need to tell you a little bit more about finding other kinds of patterns in the primes, not just pairs of twin primes. So I made myself a number line. Here's my number line. And I colored the primes a different color. So I hope you can just about see that the primes are in red there and the non-primes are in black. And then I made myself a twin prime detector. So this is a piece of card, and I've just cut out holes. It's a little bit like an old-fashioned punch card. And the idea is that you can slide it along the number line and detect pairs of twin primes. So, okay, 1 and 3 is no good, 1's not prime. 2 and 4, not so good. 3 and 5, twin primes, great. 4 and 6, no. 5 and 7. So I can take my piece of card, slide it along the number line, and the Twin Primes Conjecture predicts that there are infinitely many positions of the card where both of the visible numbers are prime. Right? So the Twin Primes Conjecture says, as you slide a card along, there are infinitely many positions where both of these numbers are prime. And when you start looking at it that way, you start thinking, well, what if I used other kinds of punch card instead? Here's one I made earlier. So this one's got 3 holes, and I've got a slightly larger gap. And again, I can slide it along and see what happens. So no, 2, 4, 7, no good. 3, 5, 8, no. 4, 6, 9, no. 5, 7, 10, no. So again, the goal is to slide it along and find infinitely many positions where all of the visible numbers are prime. So far, I have found no positions of the card where all of the visible numbers are prime. And actually, if you look carefully, we can sort of see what the problem is here. So if you look at the 2 numbers on the right, one of them's odd and one of them's even, always. So they differ by 3. So if I start with odd or even, I get the other one afterwards. So the problem is, we know 2 is the only even prime, so no matter how I slide this along, I'm always getting 1 even, 1 odd. I'm not getting primes. So this was a very bad choice of card. But I could try a more sensible choice of card where I fix it so that all of the visible numbers can be odd simultaneously. Like 3, 5, 7. In fact, here, all of the visible numbers are prime. So this is great. This is a good triple from our point of view. And then I can slide it along. And there's really no point in focusing on even numbers because we are not interested in even numbers bigger than 2. So 5, 7, 9, close but not quite. 7, 9, 11. Okay, 9 is a problem here. So let's keep going. 11, 13, 15. No, now 15 is the problem. Okay, so I found 1 triple so far where all of the visible numbers are prime, but I'm sliding it along and I'm not having much joy. So what's going on? It's not the problem of having odd and even because all of the visible numbers are odd. Actually, the problem turns out to be multiples of 3. So the problem, if you look at the problematic numbers, they were 9 and 15, and it turns out if we keep going, that keeps being the problem. So why do we always get a multiple of 3 that's visible? I like to think about this in terms of bars of chocolate. So every number in the world is a multiple of 3, or 1 more than a multiple of 3, or 2 more than a multiple of 3, as illustrated by bars of chocolate. So every number is one of these, and if we look back at those triples, one of the visible numbers is of each type. So looking at the bottom, 15 is a multiple of 3, 13 is 1 more than a multiple of 3, 11 is 2 more than a multiple of 3. 5, 7, 9, 5 is 2 more than a multiple of 3, 7 is 1 more, 9 is a multiple of 3. We always seem to get one of each type. And if you think about it, you can think about it with the bars of chocolate. That's sort of inevitable. If you start with a multiple of 3, that's bad. If you start with a number that's 1 more than a multiple of 3, when you add 2 on, you get a multiple of 3, and so on. So what we can see by thinking about bars of chocolate or via some other way is that we always have one of each type of number, and that means that we're somehow doomed always to have a multiple of 3 that we can see. And the problem is the only prime multiple of 3 is 3. So In fact, it was the same kind of thing with the odd and even. It's just that we talk about odd and even rather than being a multiple of 2 or one more than a multiple of 2, but it's the same kind of thing. So this card, we can see we're definitely not going to have infinitely many positions of the card where all of the visible numbers are prime. In fact, the only one that works is 3, 5, and 7. You can kind of convince yourselves of that. And you can imagine if I had a card with more holes, that I might find that the problem was the prime 11. So there are 11 types of number, like 11 bars of chocolate. If you think about division by 11, you could be a multiple of 11, or 1 more than a multiple of 11, or 2 more than a multiple of 11, and so on, up to being 10 more than a multiple of 11. If your punch card somehow means that the visible numbers between them always include one of each type, you are always going to have a multiple of 11, and the only prime multiple of 11 is 11, so that's going to be no good. So if our game is think of punch cards where there are infinitely many positions of the card for which all of the visible numbers are prime, we need to somehow rule those ones out. And mathematicians have a definition for this. So we talk about a punch card being admissible if there's no problematic prime. So we've seen a couple of examples of punch cards that are not admissible. So the first one was this, I've got 11, 13, 16 here, where we always had an odd and an even. The problem was the prime 2. The 9, 11, 13, the one I'm holding here, the problematic prime was 3. So non-admissible punch cards, we can rule out immediately from our game because somehow they are not going to work. We can see straight away they're not going to work. The admissible punch cards, we can't rule them out, but we don't know for certain that they do work. So the first punch card I've got here is just the Twin Primes detector. So we think there are infinitely many positions of the card for which both these visible numbers are prime. We can't yet prove that. I've got another example of a visible card here, so you can check that there aren't any primes that are going to cause this card problems. All that means is that we can't rule it out. We don't yet know that there are infinitely many positions of the card for which all of the visible numbers are prime. So that was one of those things where don't worry if you didn't take in the details. What we need to know is that admissible punch cards are good, but still a work in progress. So Zhang's work used this idea of admissible punch cards. They're not called punch cards in the mathematical literature, they're called sets, so admissible sets. And what Zhang proved was that if you've got an admissible punch card with enough holes, and by the way, that means loads, so you've got a punch card with loads of holes, there are infinitely many positions of that punch card where at least 2 of the visible numbers are prime. So we'd like to have all of the visible numbers prime. That's way too much to hope for. But at least 2 of the visible numbers will be prime. And then crucially, there is an admissible punch card that has enough holes where the length of the card is at 70 million. So as I take this card of length 70 million and slide it along the number line, Zhang's theorem says there are infinitely many positions where at least 2 of those visible numbers are both prime. It might be lots more than that. We think it is lots more than that. We know at least 2. So it might be these 2 over here and these 2 when we've moved the card further down. So that's why we don't know exactly what the gap is. All we know is that some 2 of these visible numbers will be prime. And when you think about the theorem in that way, so you sort of start having opportunities to start improving on this, because when people started reading Zhang's paper, it became clear 70 million was not the best answer that his argument would give. And you can totally see why that is from Zhang's point of view, because from Zhang's point of view, it doesn't matter whether his paper says 70 million or 65 million, right? It really doesn't matter. What matters is being the first to get your paper out and writing a paper that is clear enough and comprehensible enough that other people are going to read it. So he focused on writing this very clear paper rather than spending extra time trying to see, well, what's the best possible number? But then other people want to go, well, what can I do? Because if I could use a narrower card that still had enough holes, then we get a better bound straight away. If we could somehow show that we could get away with having fewer holes in our punch card, then we could have a narrower punch card and we'd improve. So people started trying to improve on this. And this really started in public. So a couple of people started writing papers, but it really took off when Scott Morrison wrote a blog post called I just can't resist. There are infinitely many pairs of primes, at most 59,470,640 apart. And he explained how he'd slightly tweaked Zhang's argument to come up with this number. And of course, everybody else then wanted to have their moments of having the world record for this problem, right? This is one of the most famous unsolved problems in the whole of mathematics. If you have an opportunity to hold the world record for 5 minutes, wouldn't you? So people started commenting on Scott Morrison's blog post and say, well, what if we do this? What if we do that? Maybe we could get this other thing. Somebody wrote a paper a while ago. I think that might help. And this was sort of going to get out of hand because how do you have that kind of mathematical conversation in public? You sort of have to be a little bit organized about it. Unfortunately, there was a way to organize that conversation. So a few years earlier, a mathematician called Tim Gowers, who has a blog that's very, very widely read amongst mathematicians and those beyond the academic maths community. So he wrote a blog post called, "Is Massively Collaborative Mathematics Possible?" And he had this kind of vision for a collaborative project on a much larger scale than is usual in maths. In maths, it's kind of unusual to have a paper with 5 authors on it, even in pure maths. There's lots of small groups, but not these big groups. So Tim Gowers wanted to know, could we have a much bigger group where somehow everybody works on their little bit of the project, but no one person has to think too hard? So sort of a little bit like an ant's nest. Everybody's doing their own thing. The collective effort is great. No one person is organizing it. And he put out this post and described some rules for how this would work, how you should behave in the conversation, if this led to a publication, who would get the credit, all of those kinds of things. So he thought through that very carefully. And he proposed a project for polymath to work on. So there's a joke in that name somewhere. So the idea was polymath was going to work on this particular research problem, which was a genuine research problem. People in the area had wanted to solve this problem for some time, had thought hard about it. And I think to everybody's surprise, within a few weeks, polymath had proved this result. They'd found a new way of proving this conjecture. They'd solved the problem, which was kind of unexpected. And it seemed that collaboration had proved very effective for doing that. So that led on to other polymath projects, trying out different kinds of problem. And one of the things here is it's a very new way of working. If this is all happening in public, on blogs, on wikis, anybody can join in, it's all in public. So what kind of problems lend themselves to that way of working? So there's a lot of trying this out over the years. Some projects were more successful than others. But it meant it was very natural when this came along to say, well, let's have a polymath project to work on this. So Terry Tao, who is another mathematician with a very widely read blog, who'd been involved in the earlier polymath project, said, let's have Polymath 8, a project on bounded gaps between primes. And I've included this quote. This is his description, his proposal for what the project should do, because I think it's quite interesting. Yes, the first one is improving those numerical bounds. We've got 70 million, we've got Scott Morrison's bounds, how far can we go? But the second aspect of the project is understanding what Zhang did, really kind of getting to grips with the details. What were his new insights that other people hadn't had before? Could those be simplified? Could they be streamlined? How did it fit with what other people in the area had done? Mathematics doesn't happen in isolation. Yes, Zhang worked by himself on this, but he built on what other people had done. It was going to feed into other things. So what were those relationships? So this polymath project started, and of course, lots of people were quite keen to join in because their opportunity to be part of holding the world record on this very famous problem. And it's all in public. It's all on blogs. It's all online. You can still find it. I encourage you, if you're interested, to have a look. So what I've done here is taken some screenshots from the wiki that was set up for the project. This is like a league table for the best known things. So I know it's hard to see on the screen. I'm not expecting you to kind of see all the details. The crucial column, this is comments. The crucial column is the next one across, which is it's called H at the top. That's the crucial number that we're interested in. So the second row here is Zhang with H 70 million. There are infinitely many pairs of primes that differ by at most 70 million. And then this number tumbled. So Scott Morrison is quite high up on that list, sort of fairly early. And then this number just tumbled through the summer of 2013. So we've got to June 2013, and already the number of digits is decreasing significantly. Even if you can't read the number, they're getting much smaller. And it kept going. Actually, this was quite an interesting moment on the league table. I don't know whether you can see, lots of these numbers have been crossed out. Because what would happen would people come along and say, well, I think I could get this number. Here's a link to the blog or wherever that I've explained the argument. And then other people will come along and check and go, yep, that seems great. Or hang on, I don't understand this bit. There seems to be a problem there. And there was a whole sequence of results here that turned out to be problematic. And they were all based on a preprint, like a draft paper by one of the experts in the area, Janos Pins, who put up this draft paper. And people said, oh, that's great. Using these ideas, here's how we can improve the bounds. And it turned out there was a mistake in the draft. So these bounds had to be retracted. Actually, the paper went on to be interesting and useful and have consequences, but not quite for these numerical bounds. And I think one of the really interesting things about this polymath way of working is that we get to see all of this. Normally, when mathematicians work on a problem, They write up their nicely polished solution at the end for publication. What appears in the journal, what appears in the paper online, is this is how I did it, this is what worked, this is all cleaned up. You don't see all the rest of what if we try this, what if we try that, oh, whoops, that thing didn't work out, I got that bit wrong. All of those other kinds of things, they get wiped off the board at the end of the project. They get put in the recycling bin or put in a pile in the office to look at later. Gauss, one of the great number theorists of the past, commented that the architects don't leave their scaffolding behind, and this is somehow what mathematicians do. But actually, that's quite frustrating, because it means if you've got some famous problem that everybody's working on, maybe there are 3 obvious things to try to solve this problem, and everybody who works in this problem tries those 3 obvious things before they get on to maybe having some new ideas. Having something like this, there's a record of everything that you've tried, so other people can see, oh, actually, that seems to have been a bit of a dead end, or that looked promising, but they didn't pursue that. Maybe I can use that. The good news is that after those bounds were retracted, there was then a continued improvement, and it just dropped and dropped through the summer of 2013. And I'm sure that that progress would have happened without polymath, but polymath was a very good way of streamlining it and making it more efficient. Otherwise, you'd have had maybe individuals, maybe small groups of collaborators putting out papers saying, well, I can get this bound, I can get this bound, I can get this bound. It's kind of race. So doing it collectively was a much more efficient way of doing it. And through the course of doing it, it became clear that the different ways to improve on the bound drew on different types of expertise. So some people were very good at getting their computers to do a particular kind of calculation to find narrow punch cards with lots of holes. Other people were more interested in the theoretical aspect of how can we decrease the number of holes? How can we really understand this argument? So in order to go forwards with the story, I want to go back a bit to before Zhang. So back in 2005, when there was the previous big breakthrough on this problem, which came from Goldstone, Pintz, and Yildirim, in fact, the same Pintz I just mentioned. And Goldstone, Pintz, and Yildirim proved that if the Elliott-Halberstam conjecture is true, then there are infinitely many pairs of primes that differ by at most 16. That's like 16. The trouble is, we can't prove the Elliott-Halberstam conjecture. So this sort of feels slightly disappointing. At the time, this was super exciting because it was progress on a problem that had seemed intractable. They'd found a way to do something, make some progress. And actually, assuming a conjecture you don't know how to prove is a really good way of making progress in maths. Sometimes if you can isolate that the problem is here, and you say, well, I'll allow myself to assume that and deduce this from it, that could be a really helpful way of focusing attention on what's the important thing here, what are the key questions we need to do. So in number theory, often the assumption you want to make is called the Riemann hypothesis. This is another of these famous unsolved problems. So there are lots of papers in mathematics that start, if the Riemann hypothesis is true, then whatever. In the early part of the 20th century, a group of mathematicians proved that if the Riemann hypothesis is true, then something or other is true. And then a few years later, another group came along and proved if the Riemann hypothesis is false, that same statement is true. Isn't that beautiful? We know it's true, we're just not sure which proof. The go-to conjecture in this particular area is called the Elliott-Halberstam conjecture, which is a conjecture about the distribution of prime numbers. So let me try to give you a little bit of a flavor. I don't want to go into the technicalities, but let me try to give you a flavor of the Elliott-Halberstam conjecture. So what I've got here is the prime numbers, but instead of 10 columns like I had earlier, this time I've got 6 columns. And I think this is quite visually striking, right? Patterns start to leap out. So the 4 column and the 6 column appear not to have any primes. Does that continue if I go below the slide? Yes, because all the numbers in the 4 column and the 6 column are even, we know 2 is the only even prime. So in fact, 2 is very lonely in its column. 2 is the only even prime, no matter how far down we go, don't get any more there. 3 is looking pretty lonely too. But we know that the only multiple of 3 that's prime is 3. And if you look carefully, this column, these numbers are all multiples of 3. So these are the multiples of 6, the even multiples of 3. These are the odd multiples of 3. So what this slide and that little bit of reasoning shows is that apart from 2 and 3, every prime in the world is 1 less than a multiple of 6 or 1 more than a multiple of 6. Isn't that nice? It's so good, I'm going to say it again. Apart from 2 and 3, every prime in the world is 1 less than a multiple of 6 or 1 more than a multiple of 6. And once you know that, then you can start asking more questions about the distribution of the primes. Like, we know there are infinitely many primes. We saw Euclid's proof of that earlier on. Are there infinitely many that are one less than a multiple of 6? Are there infinitely many that are one more than a multiple of 6? There must be infinitely many in at least one of those two. But is it just one or is it both? So it turns out there are infinitely many primes in both of those columns. So this one turns out you can prove quite nicely by adapting Euclid's argument. This one takes a little bit more work. And you can ask other questions, like if you were a prime number, would you rather be one less than a multiple of 6 or one more than a multiple of 6? So I guess the more mathematical way to say that is if we look at the numbers up to 1 million or 1 billion or whatever, are there more primes that are one less than a multiple of 6 or more primes that are one more than a multiple of 6? And it's not really clear that the primes should favor one of those options over the other. So we kind of expect them to be pretty evenly distributed. So I think up to 90 here, they are pretty evenly divided between those two columns. You don't expect them to be exactly even, but pretty close. So the Elliott-Halberstam conjecture is a prediction that, yes, they should be about evenly divided between those two columns, and a whole bunch of other similar predictions for other numbers of columns. So if I've got 7 columns or 101 columns or whatever, I can predict which columns should have infinitely many primes. In fact, we can prove that. That turns out to be a harder theorem to prove, but a really interesting theorem. Which columns have infinitely many primes? And the Elliott-Halberstam conjecture says that the primes should be pretty evenly distributed between the columns where there are infinitely many primes, sort of for all of these tables at once. So that turns out to be hard, by which I mean we don't currently know how to prove it. But if you take that data, that kind of prediction about the distribution of the primes, you can feed it in to this argument using sieve theory, which is what Goldstone, Pince, and Yildirim did. And they were able to say, well, if this is true, then we can prove this result. So there's kind of a whole family of these conjectures for different parameters, and they sort of needed a particular parameter where they couldn't prove it. What Zhang was able to do was to slightly weaken the assumption you needed to make, so something slightly weaker than the Elliott-Halberstam conjecture, and crucially then he could prove that required fact about the distribution of the primes. So he took the Goldstone, Pince, Yildirim kind of idea and then adapted it in a really ingenious way to make it work out. So back to polymath. So by August 2013, the Polymath project had managed to prove that there are infinitely many pairs of primes that differ by at most 4,680. I love the fact that some of you are looking impressed. If I'd said 4,680 half an hour ago, you'd have said, that's rubbish, you wanted 2. But it is big improvement on 70 million, right? It's fantastic, very efficient. The trouble is, by August 2013, so Terry Tao said that the low and medium hanging fruit's been picked. All those little tweaks you could do to Zhang's argument, all those getting a computer to help out a bit, that are sort of apparently all being exhausted. And it seemed like there was going to need to be a new idea. And the nature of research, of course, is you never know when the next idea is going to come or where it might come from. In this case, it didn't take very long. In fact, it was November 2013. And a mathematician called James Maynard was able to show that there are infinitely many pairs of primes that differ by at most 600. Big improvement. James had recently finished his PhD. He's now one of our colleagues in Oxford. He'd gone to Montreal as a postdoc at the time. And through his PhD work, he'd become an expert in this kind of area. And he found that he was able to go back to the work of Goldstone, Pince, and Yildirim and find a new way through. So not only did his argument give a better number than the work of Zhang and Polymath, but it also gave a slightly simpler argument. And that's the kind of dream scenario, right? When a slightly easier argument gets you a better bound, you're sort of on the right track with understanding. One of the nice things about this bound is that it's small enough that I can show you an admissible set that works. I do not expect you to take in these numbers. This is like the recipe for the punch card, the admissible punch card. So there are infinitely many positions of this punch card where at least 2 of the visible numbers are prime. And I'm only putting this up to make the point that it's a small enough set that I can fit it on the screen. So James Maynard could show there are infinitely many pairs of primes that differ by at most 600. Of course, then Polymath gets very excited and says, well, that's great. What if we look at James Maynard's work and understand that? Can we do even better? And so this league table resumed. The bound kept dropping and dropping. By April 2014, so a few months later, Polymath could show there are infinitely many pairs of primes that differ by at most 246. And to the best of my knowledge, that's the state of the art. You'll notice that April 2014 was a little while ago. So Polymath have written up their paper. James Maynard has written up his paper. I should say about the same time as James Maynard had his ideas, Terry Tao had some very similar ideas, that same kind of approach for adapting the sieve theoretic argument. But Terry Tao's arguments gave just slightly less good numerical bounds. What James Maynard and Terry Tao did both manage to do was find an argument that would deal with other clusters of primes as well. So not just pairs of primes that differ by 2, but if you want 3 primes very close together or 4 primes close together, they started to be able to make progress on those kinds of questions. So Polymath have been working on improving those bounds too. And if you go and look at the league table, you can kind of track down those bounds. There's still the game of, if we're allowed to assume the Elliott-Halberstam conjecture, what's the best bound we can get? So Goldstone, Pitts, and Yildirim back in 2005 could show if you assume the Elliott-Halberstam conjecture, then there are infinitely many pairs of primes that differ by at most 16. So James Maynard's argument gets you down to 12. So if you assume the Elliott-Halberstam conjecture, there are infinitely many pairs of primes that differ by at most 12. If you assume a stronger and more controversial form of the conjecture, maybe you can even get all the way down to 6. That's like tantalizingly close to 2, right? So near, and yet so far. And the trouble is that within sieve theory, there's a well-known kind of problem that means that people don't think that the arguments that get down to 6, even assuming this conjecture, will get down to 2. It's called the parity problem. It's because the sieve theory isn't very good at dealing with only looking for numbers with an even number or an odd number of prime factors. There's this kind of technical difficulty that means that 6 is like a brick wall. So there are going to need to be some new ideas. So where next? Well, there's all this work on the Twin Primes Conjecture to look at. So of course, people are trying to improve on the bounds. People are taking the arguments that have been developed and saying, well, what else can we do with those? What other problems can we solve with these kinds of ideas? Surprisingly, sometimes the answer is problems about large gaps between primes. So how large a gap can you have between primes? Well, you can have as large a gap as you like. If you want a gap of 100 between 2 consecutive primes, you can arrange that. That's not too difficult. That's a kind of problem that might appear on an undergraduate problem sheet as a nice go away and think about this kind of thing. The interesting question is when those gaps are larger than the average. So on average, the primes get more spread out, and the gaps can be as large as we like. But amongst primes around 1 million, we sort of know what the average gap looks like, and sometimes the gap can be much smaller, like 2. Sometimes the gap can be much larger. So you sort of say, well, for primes around this size, can the gap be much larger than the average? And this was a long-standing problem. It was a problem posed by Erdős, who was a prolific poser of problems. And he liked this problem and thought it was so difficult that he attached quite a large monetary value to this problem. So Erdős liked to offer cash prizes in return for problems. And the amount of cash he was willing to stump up, depending on how hard he thought the problem would be. Erdős died some years ago now, but a friend and colleague of his has been honoring these promises subsequently. And simultaneously, 2 groups made progress on this, how large can the gap be, when can it be larger than the average gap problem. So one of those groups was a group of 4 mathematicians involving, in fact, Ben Green here from Oxford, Terry Tao, plus a couple of others, Kevin Ford and Sergei Konyagin. The other group was James Maynard, who they came up with these completely different approaches, each based on things that those groups were experts in before. And what's extraordinary is that James Maynard took his work on understanding small gaps between primes and used it to understand large gaps between primes, which is very unexpected. So there's lots of potential for seeing where these ideas can take us. Even if they're not proving the Twin Primes Conjecture, they're all building our understanding of prime numbers. I do believe that the Twin Primes Conjecture is true. I do believe we will manage to prove it. I've got no idea when. It might be next week, it might be next year, it might be in 20 years' time when one of the young people in the audience today has solved it. I'm looking forward to finding out. Thank you very much.